we're calling this section 5.4, mathematical induction. It's probably going to be like a purely like bonus section that can lead to some bonus points on the eventual exam. Mathematical induction is a strategy of proving something. So we have a statement involving n, like the variable n or the positive integer n, and then we want to prove that this statement is true for all possible positive integers and positive values for n. As an example, I'll go back to here in a second, but this is an example, like you can see right below. Use mathematical induction to prove that this 1 plus 2 plus 3 plus, and then whenever you wanted to stop, if you wanted to go all the way to like plus 99, if you wanted to go to 200, if you only wanted to go to 50, you know what I mean? Let's prove that this sum is always going to actually equal that. And as it turns out, this is actually one of our formulas. Like this is the formula for sigma I that we've probably already written down as like another opportunity for bonus points or whatever. But so we're going to prove stuff like this. Anyway, obviously the first thing you want to do is jot this down, and it might be necessary a few times in this video to pause the video to give yourself time to write down whatever's on the screen, or you want to go back and rewatch something, you know what I mean, then pause and go back or something. But I'm not really gonna I'm not gonna like go out of my way here to pause my instruction and let you copy things down. So just be ready to pause and go back if I move on to the next page too fast. It's not a big deal, it's a video. So here are the basic steps of proving something by mathematical induction. Step 1 is you want to show that the base case is true, like the very first case is true. Then we have to do this really fancy induction step where like you can show that if S sub k is assumed to be true, then that automatically makes the k plus 1 case true. Like you're probably thinking, what? Like if you have some random like generalized n equals k case, like okay, like so case 1 is true. You could show that case 2 is true and that case 3 is true, but you can't show every case. Like this one, you could very easily show that when n is 1, when the left side is just 1, then it's going to be equal to 1 times 1 plus 1 all over 2. In fact, that's what I do here in the base case. That's the first step of this proof, is to show that the base case is true. But you could also show very easily that, okay, what about when n equals 2? The left side would just be that, 1 plus 2, and the right side would be 2 times 2 plus 1 all over 2. And you could very easily show that that works out to be 3, which is, 1 plus 2. You could also then show that this whole thing works out when n equals 3, and when n equals 4, and when n equals 5, and n equals 6, and n equals 7, and n equals 8. You could show all of that. Wouldn't even take you that long. But even if you literally write out the first 100 cases and they all work out, you know what I mean? 1 plus 2 plus 3 plus 4 plus 5 plus 6 all the way to like plus 99. And it turns out to be 99 times 99 plus 1 over 2. And then you go all the way to 100, and that's, that whole sum. And it actually ends up equaling 100 times 100 plus 1 over 2. It doesn't matter. Like we want to show this for all cases of n. And you can't list them all. So that's why we have to do this red step where it's like, okay, let's assume it's true for some generalized K case. And if that leads us to be able to show that the K plus 1 case is true, that inductively shows that any case can be true, because K could be anything. And, if that's true, which leads to that being true, then that keeps it going inductively forever. Anyway, here's how this works out. So on this example, and again, if you need to pause the video to write that down really quick, but I'm moving on to step 2. Let's assume that this is true. We are going to assume that this is now true, that 1 plus 2 plus 3 all the way to whatever, K, is actually equal to this. All right? Again, pause the video if you need to write that down. But so here's the induction step. Okay? We have to now show that we can now say beyond a shadow of a doubt that we go all the way to K plus 1, the K plus 1 case, and it holds true, right? So we have to show that, okay, when we take the left side all the way to, K plus 1, that it's actually going to equal this right side, where, again, we go all the way to, where n is actually now K plus 1. So it's like K plus 1, and then that's K plus 1 plus 1, all over 2. So we're going on the left side, we're going all the way to K plus 1, and n equals K plus 1. And on the right side, we're going all the way to n equals K plus 1. So as long as we can now show that the left side and the right side are equal, we got it. Like proof over. All right? Now, here's where the assumption, I'm using red here on step 2. Here's where my assumption comes into play. Remember, I am assuming that this does in fact equal that. So now, in this step right here, I bring that back out and I use that. See how I put this part in red? Remember, we just got done assuming that this equals, ready, that. So hopefully the use of color here helps you out. So this, in fact, does equal that. And now, from here on out, it's pure algebra. Obviously, right here in this bubble, K plus 1 plus 1. I hope I just did K plus 2. Yep. And, it looks like that. And again, like with a little bit of experience, you know when to keep going with things. But it looks like I took these two bubbles and I probably actually foiled them together. So foil, right? And it turns out I get that, which is pretty much going to carry down all the way. But okay, but what happens on the left? So on the right, it wasn't that tough to kind of just simplify that and then foil together and end up with, that. But on the left, what do I do? How do I, what can I do on the, and again, this is pure algebra, showing that the left side is in fact going to equal the right side. Well, what I'm going to have to do is actually add those quantities together. That's a fraction. What I'm going to have to do is make common denominators here. So if I give that a denominator of 2, right, aren't you going to have to multiply this by 2 over 2? So, and then, okay, over here it looked like I just distributed k times k, I distributed the k. You know what I mean? So that gets me to here. And now that I have common denominators, they can now add together since they now have common denominators. And boom, bam, did it. So now these are exactly the same. And once you have that, you're done. So induction step, just a quick recap, k plus 1. We utilized the assumption we made in step 2. After that, it was pure algebra, okay? To just make the left side and the right side literally blatantly match each other. Again, pause the video if you're not done writing that down, but let's run through the next example really quick. So now, this is the sigma I squared formula. This is a proof that our sigma I squared formula also works. You know what I mean? 1 squared plus 2 squared plus 3 squared plus, whenever you want to stop, that actually equals that, So step 1 is the base case when n equals 1. So on the left side, that's only going to be the 1 squared term. And on the right, where we just literally let n equal 1, we just got to do a quick check to see okay, 1 squared is obviously, 1. But does this right side all equal just 1? Well, 1 plus 1 is 2, 3, yep. So the base case checks out. And then it comes time to do the assumption, right? Where we assume that this whole thing is going to be true for some n equals k. All right? For whatever, For we checked case 1. Now let's make an assumption for case k, little k. All right? So we assume that's true. Now in the induction step, now we have to show that this is true for case k plus 1. So we go 1 squared plus 2 squared plus 3 squared plus blah, 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 blah. Whenever we get to k squared, and then of course right after that is k plus 1 quantity squared. And then once again, over on, wrong direction. Over here, we're just going to plug in k plus 1 wherever we see n, which gets us this. All right? So what do we do now? Well, on the left, it's definitely time to apply the assumption. Now you have to use that assumption. We just got done assuming that this part, 1 squared all the way to k squared, was equal to something. So we can now, all right, I don't know if you need to write that out again, but, now we can actually replace all of that with what we assumed it to equal, So now it's just pure algebra, like I said. So over here, obviously that's just going to be k plus 2, you know what I mean? And then over here, you'd probably have to distribute the 2, 2k plus 2 plus 1. Ends up being 2k plus 3, And I already had started, foiling? So it looks like I foiled those two bubbles together to get that. And again, I know I'm going kind of fast, probably faster than you can write, but again, pause and rewatch certain parts, whatever you need to do. So on the right, we're just kind of cleaning this up. We're multiplying, you know what I mean? On the left, it looks like we're going to have to, we're probably going to have to do that multiplying right there. The k times k plus 1 and then times 2k plus 1. But overall, aren't we going to be making common denominators to actually do the adding? So that's my next step. Oh my gosh. Okay. All I did here was I distributed the k. That's all I did. Over here, wow, I definitely took some liberties. Because k plus 1 squared, I foiled that. k plus 1 times k plus 1. But then I also multiplied by like 6 over 6. I also did that, like 6 over 6. Sorry for the sloppy mouse writing, but so this was like k squared plus 2k plus 1 when I FOILed. But then when I multiplied by 6, it became 6k squared plus 12k plus 6. So a couple things at once there. But I'm trying to save some writing. Now over here on the right, there's some more distributing to do. I know you're having a lot of fun right now, but you know, after you do all of this distributing, I think the final result is that. Okay, when you got to like do all this distributing, you know what I mean? And finally you can like, wait, what else was there to do? Oh, I had to do the FOIL there, and then I was ready to actually add. See that now they have common denominators. Again, once you apply the assumption, like once you write that down, it's pure algebra from there on out. Just trying to show the left side is actually equal to the right side, okay? So all that algebra. But again, pause the video if you still need to jot that down. But one more example, and it goes like this. Let's see what this example is. Use mathematical induction to prove that 2 is a factor of n squared plus 5n for all n. That's a classic mathematical induction sort of thing to prove. So here we go. Step 1. Let's show that it's true for n equals 1. So is 2 a factor of 1 squared plus 5 times 1? It either is or it isn't. 1 squared plus 5 times 1? Okay. So is 2 a factor of 6? Of course it is. So that checks out for the base case. And then here's where we go from there. Check it out. Now we have to assume that 2 is a factor of k squared plus 5k. All right. But what does that even mean? Like, what does that mean? Like, you understand, I mean, I hope you understand how, like, you know, why 2 is a factor of 6. But what does it mean for 2? Like, what does it mean mathematically for 2 to be a factor of k squared plus 5k? How can we write that out, like in like math talk, math speak, you know? Doesn't it mean basically this? That 2 times something is k squared plus 5k? You know, I'm using this random variable p. You know, you can use whatever, I guess. But, I mean, isn't that what that means? If 2 is a factor of that, then 2 times something equals that. But you know what? Not just any something. Doesn't p have to be like a nice integer? Yeah, it does. So this is like just being a little bit more thorough in our math, our sophisticated math proof. But yeah, like you know what a factor is. You know, that means 2 times something is that. Okay? Now, obviously in step number 3, we're going to have to use that to our advantage because, you know, we have to assume that, and now here we go. So in step 3, now we have to prove that 2 is a factor of k plus 1 squared plus 5 times k plus 1. All right? So what do you think we're going to do? You know, we're probably going to expand that and like FOIL, you know, as well as distribute the 5, right? So this is like, you know, there might have been a step in between, you know, k squared plus k plus 1, but ultimately it's k squared plus 2k plus 1. And then, of course, those combine. Oh, wait a second. I was a little bit too antsy here. Look at this. We have to be looking for a moment to apply the fact that k squared plus 5k is 2 times something. So rearranging this stuff, 2k, look at this, 2k plus 5k, or I mean k squared, what am I saying? Yeah, k squared. What the heck was I talking about there? So k squared plus 5k, so those two terms together, you could kind of put off on the side, because again, what did we just get done assuming that was equal to? 2p, right? So we have to basically now show that 2 is a factor of that. And here's how we do it. We factor out a 2, because now we can show that this is 2 times something, which means it's a factor of 2. Because p plus k plus 3 is definitely an integer, and so, that's that. So those are 3 pretty good examples. Obviously, the third example, this third and final example, was a little bit different than the first couple examples, but, So it's like, really 2 types of examples, but 3 pretty good examples. So hopefully that helps you get a pretty good understanding of proof by mathematical induction.